Collecting gases over water. In order to determine the rate of photosynthesis, the oxygen gas emitted by an aquatic plant was collected over water at a temperature of 293 K and a total pressure of 755.2 millimeters of mercury. Over a specific time period, a total of 1.02 liters of gas was collected. What mass of oxygen gas in grams was formed? In this problem, we're given a temperature of 293 Kelvin, and we're given a total pressure of gases of 755.2 millimeters of mercury in a container that has a volume of 1.02 liters. And we're asked to find the grams of oxygen gas formed. In our conceptual plan, we will first use Dalton's law of partial pressures. Dalton's law says that the total pressure of gases in a mixture is equal to the sum of the partial pressures. So the partial pressure of gas A plus the partial pressure of gas B plus the partial pressure of gas C, and so on. So this is Dalton's law. In our example, we have two gases. We have the oxygen gas, which is what we are trying to determine the grams of. And we also have water vapor, because anytime you have a liquid, some of it will evaporate, and in a closed container will generate a pressure of its own that we call the vapor pressure. Now this vapor pressure is determined only by the temperature. In this case it's 20 degrees C, so we can look up in a table of vapor pressure versus temperature and find that the vapor pressure of water under these conditions is 17.55 millimeters of mercury. Once we have the partial pressure of the oxygen, we will then plug into the ideal gas law to determine the number of moles of oxygen. So this is just PV equals nRT, in which we know that R is 0.08206 liters times atmospheres per mole K. Knowing the number of moles of oxygen gas, we can convert that to grams simply using the molar mass of oxygen. which is 32.00 grams per mole. So now we are ready to solve. The pressure of the oxygen is equal to the total pressure minus the vapor pressure of the water at 20 degrees, and this is equal to 755.2 millimeters of mercury minus the vapor pressure of water, 17.55 millimeters of mercury, which gives us 737.65 millimeters of mercury. A number that is good to the fourth significant digit. Now, in order to utilize this in the ideal gas law, we have to convert that to atmospheres. So we'll take the 737.65 millimeters of mercury and use the relationship that 1 atmosphere is 760 millimeters of mercury. So millimeters of mercury cancel, and this gives us our number of atmospheres, which is 0.97059 atmospheres. Again, this is good to the fourth significant digit. Now we can plug into the ideal gas law, PV equals nRT, and solve this for the number of moles of oxygen. So the number of moles of oxygen will equal the partial pressure of the oxygen that we just calculated times the volume divided by the gas law constant R times temperature. So this equals 0.97059 atmosphere times our volume of 1.02 liter divided by the gas law constant R, 0.08206 liter atmosphere per mole K times our temperature of 293 K. Temperatures cancel, volumes cancel, atmospheres cancel, giving us our answer in moles, which is 4.1175 times 10 to the minus 2 mole. A number good to the third significant figure. So we'll now take this number of moles of oxygen and convert that to grams of oxygen using the molar mass. 4.1175 times 10 to the minus 2 mole of oxygen times 32.00 grams of oxygen per mole of oxygen, and this equals 1.32 grams of oxygen. Now we should check this answer and ask ourselves whether this is reasonable. We have approximately a liter of gas, and if the conditions were STP conditions, we would know that a liter is about 1/22 of a mole. If we divide 32 grams of oxygen, 1 mole of oxygen, by 22, we arrive at an answer of 1.45 grams. And so our answer of 1.32 grams of oxygen is quite reasonable.